design. First of all, I would be really thanking the IEEE Vizag Bay section to opportunity. Talk on.
Maybe little louder, Chaitanya. Your voice coming little slow.
Okay. So good evening, everyone. So first of all, I would like to convey my sincere thanks for this great opportunity. Give a small talk on 5G waveform design. And I am really grateful to the IEEE Vizag Bay section. So first, we try to get introduced to what waveforms are. Sir, is my voice is fine now, or I loud? Okay.
It is okay, Chaitanya. Now it's okay.
Yeah. Okay, sir. So it all started with a classical paper by Shannon, where he has given a geometrical representation of a communication system. So according to his view, the way he has represented it, messages and the corresponding signals are points in two function spaces, message space and signal space. While a transmitter maps every point in the message space into the signal, the receiver does exactly the reverse operation. As long as this mapping is one-to-one from message space to a signal space, that is, it is a bijective thing, a message is almost always recorded the receiver. So what is a waveform? The waveform defines the physical shape of the signal that carries the modulated information to a given channel. Thus, it corresponds to a specific structure in the signal and identifies the formation of the signal. And when the signal space relies on multiple simultaneously transmitted subcarriers, it corresponds to a multi-carrier. So nowadays, this modern day wireless communications, it is heavily dependent upon the multi-carrier scheme. So let us briefly have some understanding about what is of multi-carrier modulation. A multi-carrier scheme can be mathematically represented as by the identity. Here, DMN, it is the actual message I like to transmit, refer it also as a symbol. And then we have here the index M to the time, index in the time. Likewise, N is the subcarrier index, the Fourier domain. Here we also have one more function, which is referred as a Gabor system. It is this function which will be mapping my original message in the message space to the signal space. P of t will be in the, finally it will be the signal space. So I refer this kind of function as a synthesis function. Okay? And the family of these functions we refer as a Gabor system. Okay? So a typical way how we can view a Gabor system. Okay? There we having some pulse shaping function, precisely filter will be there, and some rotating function also will be having it. Okay, so we see that here. So why the rotation is in the time domain? I am translating it in the frequency domain. So translation in the time domain is here. So I can do the translation in the frequency by this factor. Okay. So what are the fundamental elements of a waveform? There are three fundamental elements. First, we start with the questions. What to transmit, how to transmit, where to transmit. What to transmit is the message, the form of symbols. Secondly, the question is how to transmit. So for that, we go for a pulse shaping filter. So that will define in what manner I am transmitting. Then where to transmit? To transmit, I have to locate that, right? I have to keep this symbols in some given dimensions, the dimensions of time and the frequency. So I will be taking a two-dimensional plane, which is a time frequency. So there I will be positioning my symbol. Okay. So these are the three important ones: symbols or my message, pulse shaping filter, and lattice. Two-dimensional time and frequency. So now we got some preliminary understanding about what a waveform is, what a multi-carrier is. Now we try to pose this question: why we require a new waveform in 5G? Already we have seen, and we use the already existing waveform. So for that, we need to understand first the design criteria, and then we go for the need. Any waveform design deals with the methods to generate transmitted signals at the transmitter side, receive them at the receiver side through a channel. So the design criteria in general, it depends upon demands of users, channel conditions, the system, and also some technology criteria. So the design criteria change with respect to the advancement of technology. The waveform technologies which were defined from 2G to 4G cannot meet the demands of next generation wireless. Some basic demands can be speed, number of users with whom we want to support, ability related criteria also. So these kind of things like speed, mobility, number of users, all these things, when designing a particular system or 4G, we try to understand in terms of some key performance aspects. So we refer them as KPIs. Okay, so if you go to any industry related to 4G or some laboratory 5G, always they'll be you talking about KPI. So they are the key performance indicators. Now let's see the comparison of KPIs between 4G and 5G. So here are some important KPIs we have. So when we talk about 4G or 5G, first thing which will flash in our mind is what is the offering high speed. Okay, so the peak data rate. When I'm comparing the peak data rate compared to 4G, 5G, I'm expecting to be 20 times more than. Also, I want to talk about the mobility also. Some people, they want to sit in a train and then still access the internet. Okay, so I'm talking about some order 500 kilometers per. Okay, whereas in 4G it was much less, some 3 per hour, and I want to access information at much faster rate. Talking about the latency, and then this network energy efficiency is also coming into the picture. So likewise, you have these performance indicators have, and we see that from 4G to 5G, I have very ambitious goal. Like from green communication point of view, so my energy efficiency should be 100 times more. Likewise, each KPI is having each goal. Okay. So now let us see what are the application areas of 5G. Until 4G, it is only about mobile equipment. It is only about cellular mobile communication. But 5G is having much more broader areas to offer the. Here, we can broadly classify these application areas into 3 groups. First is just the increment of from 4G to 5G in terms of enhanced plan. from that, I have two more interesting application areas. So the first area is massive machine type communication. Now some machine to machine communication will happen. So in the previous case, it is user to user communication, means when I lift the phone, I call, I dial some number. I expect that on the other end, some human is there. Whereas here, in this case, it is not human. Both the transmitter and the receiver, both are machine. Okay. So for example, today we have already, India has started smart city mission, so especially from Pondicherry. Pondicherry is also listed as a smart city means it should have like a good Wi-Fi connectivity, very optimal usage of the energy it is having, means efficient usage of a street lamps, very good surveillance for security, and also very good navigation for the traffic, etc. etc. Okay. So apart from this, I have one more interesting application area, which is ultra reliable and low latency communication. Reliable, the word reliability means that no matter how bad my channel is, the communication link between the transmitter and the receiver, it will never fail. That I call it as reliability. Latency means how much time it is taking for my transmitted signal to travel through the channel and arrive at the receiver. Okay, so I want to be my communication system to be ultra reliable and low latency. One example can be self-driving car. Suppose the driver suddenly has some heart attack or some pregnant lady labor pains. So automatically the car should sense and it should switch to the automatic driving mode and look for the nearest hospital. So imagine what are the things to come. First, it has to change from manual mode to automatic mode, look for the traffic, also Google out which is the nearest hospital. So all these things should happen with ultra reliability and in a very short span of time. And also you can, one more example, you can think of it like a remote surgery. So the doctor may be in India, but the surgery is happening in somewhere on the other end of the globe, maybe Canada or Mexico. So via some remote communication, via laptop or some communication, so the doctor is giving how the operation should be done. So we know that at no point of time the communication link be lost. Okay, so these two extra areas have we created a scenario that 4G is not just mere an extension of 5G. Okay, so based on these three application areas, so we have to define Kpis that suit to the need of each of them. For example, when I'm talking about machine type communications, the most important thing for me is the connection density and to some extent the energy efficiency. Imagine how many electric poles you will be having in a big city like Hyderabad. For example, to provide Wi-Fi connection means to provide connection at each bus station or railway station. How many bus stops you will have? So traffic surveillance, how many roads you have. So connection density is going to be large, and you need to provide the power supply for all of them. They should not eat into my power. So I should have very good energy consumption management. Okay, so only medium consumption should happen. And on the other end, for your LLC, I'm more concentrating upon the mobility and latency. Remaining things I don't bother much. For the last one, the enhanced mobile broadband, which is an extension from 5G, I expect more data rate, very good quality of service, to provide service to a large number of good spectrum. But I can for me it is okay, even if the latency is more, the connection density is less. These aspects I can tolerate. So these critical requirements for these three application areas, they are some. Okay. So the 5G communication have a heterogeneous network structure, unlike the previous technology, because they are meant to provide service not only to people who are the real users, but also for various kind of equipment. These equipment, we refer them as things. That's why now the network is not just a network of huge users, it is a network of things. The word IoT. So while designing the system in this way, you should keep in mind features for each user, such as the transmission packet length, data rates, data transmission frequencies, and capacities would differ. These various requests of you users, lot of issues such as synchronization in time and frequency. To overcome this problem, it is required to design new techniques capable of utilizing the spectrum more efficiently, because we know that the spectrum is a very costly thing. So we cannot use spectrum just like that. We have to use it very judiciously. Utilizing the spectrum more efficiently, provide a high data rates, green communication point of view, consume less energy, and also to have low latency. Okay. So for 5G physical and MAC layer, we can see the building blocks. So these are building blocks we have. So first we have to decide what spectrum, then which waveform we have to provide, what kind of multiple access I'm having, frame structure, channel coding scheme, modulation, MIMU scheme, and which kind of duplex mode I have. Now nowadays we are having this concept of full duplex also, whereas in 4G it was either dependent on fusion duplex or. But in these building blocks, you see that after spectrum, second most important one is the waveform. Okay, so when I'm constructing a building, first I start with the foundation, and then I go for one building block. Only at the end I'll be talking about, okay, what about the interior design, all these things. Here you can see that from that analogy, I can make out that waveform design is one of the most important things after the spectrum. Okay. So this is a very important question we need to solve before we are going to offer the 5G services in a full-fledged manner. Okay. So until 4G, we have the multi-carrier called Ofdm. You all know it, orthogonal frequency. But for 5G, as of now, for time being, we are keeping. But we try to see, like, what is wrong with why I want to go. So till now, OFDM is the dominant technology for current broadband multi-carrier communication. WiMAX, LTE, or broadcasting. But is having some basic limitations. First limitation is the CP overhead. Because of cyclic prefix, it is directly impacting the spectral efficiency. Then it is highly sensitive to the synchronization, meaning receiver should be synchronized with respect to time and frequency. If there is some offset, then it will immediately result in the loss of orthogonality. I can no longer claim orthogonality. Okay, so it will be directly impacting my bit error rate. Okay, it means the quality of also, apart from frequency and time offsets, since I am talking about millimeter wave frequencies for 5G, even phase offset also can impact OFDM, which will be more severe. Okay, so all the three aspects of a signal. Okay, so the time, frequency, and phase all has to be highly synchronized. So this is the second issue. Last one and most important one, high peak average power rate, high PAPR. High PAPR means my signal will have huge fluctuations. See that the peak power is much larger when compared to is having direct impact on the power consumption. So, so based on some European project on power consumption back in 2014, it has that it is around the consumption is reaching around like some 10%. By 2020, it's going to be more. More power consumption means that I have to utilize it equipment that consumed power. There is equipment called power amplifier, so which will be consuming most of this power, and it is being dissipated as heat. So imagine that the all the base stations, the mobile equipment you have means present in information communication industry. All these equipment, starting from small cell phone in big base station broadcasting scenario, base stations they use power to the order of kilowatts. Okay, so they all are dissipating heat. So pumping heat into the atmosphere means indirectly to the global warming. You know, to be frank, it is not indirectly, we are directly contributing. So way back the 2014, they found that it is around 2% contribution greenhouse gas. In 2020, they have estimated that it will be doubling around 4 or 5 percentage. 4 or 5 percentage contribution global warming is an alarming thing. That's why the International Telecommunication Union has come up with some strong regulations for the future technologies. So these regulations, so we can broadly refer them as green communication. You can hear more and more that the equipment you are having in future, it should be more greener. More greener means consume less power and contribute less to the global warming. Very serious issue now. Okay, so imagine that in 5G, I'm talking about machine-to-machine communications coming. Thousands of devices will be there per square kilo in a city. See that in a 7 billion population, how much dangerous disease. Okay, then the RF impairments in communication systems, such as the power amplifier nonlinearity imbalance, they can be extremely severe for a high PAPR. Hereby, they lead to in-band and out-of-band distortion means it will directly impact the quality of my transmission. Out-of-band distortion means it will lead to spectral regrowth in the out-of-band. So I cannot use my spectrum efficiently. Also, I will be wasting. Okay, so this is on. We already mentioned that spectrum is a very costly use judicious math. An illustration. All in a figure. So for the in-band, it that whatever constellation I am having, it gets distorted, and also it gets scattered. Okay, so it will be impacting my bit rate. From the broadcasting industry, they have come up with parameter called modulation error ratio to quantify the quality of my transmitted signal. Okay, So if the modulation error ratio, if it is less than 32 dB, then it means that total broadcast failed. Okay, so this is one issue which is the in band and out of band. So for example, for some user, some spectrum located here, ideal case, so I can allocate one more user here also, but because of the spectral growth, because of RF impairments, I have to have some gap. I have to maintain some gap, means wasting my spectrum. Okay, first thing, I am wasting my spectrum, and second thing, I am having some out of band energy. So for that, see that modern day communications, they come up with something called spectral masks. So these spectral masks, they must be strictly made. So whatever spectral growth I'm having, it should be below that spectrum. Okay. So we try to discuss a little bit more about this high PAPR. Is it only for OFDM? Problem is strictly speaking, not just for OFDM. Every multi-carrier scheme has high PAPR because of central limit. Okay, so more central limit because of central limit theorem. So the peaks will start behaving as Gaussian random variables. We know that the PDF of Gaussian distribution, it spans from minus infinity to plus infinity. If I want to take the amplitude, so square my modulus square, then the amplitude can be 0 to infinity. So strictly speaking, I can have infinite peak. So I can have infinite PAPR, theoretically speaking. So this problem is there for all multi-carrier. And as already mentioned before, high PAPR poses tough challenge to RF design of power amplifier. The power consumption helps define the battery life for mobile communication. Suppose we want to have suppose we launch some satellites. So recently NASA has sent over to Mars. Imagine that the battery dies within just six months. You cannot go there simply and change the battery. So before launching it, I should keep it in my mind that it should have a long battery life. And if my signal it is having high PAPR, then it will have direct impact. Okay, so these things we have to keep it in mind. So this was first identified, this problem of high PAPR was first identified in 4G LTE. So then what they did for the uplink, for immediate remedy, like a first aid kind of thing, they have proposed single carrier FDM, increase the UE battery life, means the mobile equipment battery life. Because if you have to, if your mobile phone is consuming power like anything, then you have to sit just next to the power supply. Every time you have to keep on charging your mobile phone, and you cannot truly experience this aspect of mobility. Okay, so for that they have proposed SEM. From then they started studying some other waveforms which can tackle this issue of high power consumption and RF. So this high PAPR problem paved way for study of waveform other than OFDM or 5G. We refer these waveforms as post OFDM waveforms. So now we have understood like why we need a new wave 5G. Let us come back. So we have already discussed that the fundamental elements are symbol, pulse shape, and lattice. So out of these three, the first one constitutes the random part of my waveform, because my message can be on anything. Okay, so it has inherent random, but the remaining two, they are deterministic in nature. Okay, So whenever we design something, try to minimize the randomness. We cannot deal with too randomness. Okay. So out of the three, only the first one is random, remaining two are determined. This simplifies. So let us understand more about symbol. A symbol is a set of complex numbers in the message space that is generated by grouping a number of bits together. So my analog signal, I will be slicing it into some sequence of bits, ones and zeros. Now I map these bits into some complex numbers. Okay, some complex numbers I refer as symbols. They exist in message space. So from binary space, I'm mapping into message space. And from message space, now then I have to map again into signal space for transmission. Okay, so this is what we are doing. Message space, some number of bits are grouped and then mapped to symbol in the signal space for transmission. This number determines the modulation order, which in turn highly impacts the throughput. For example, in one symbol, if I can group too many bits, then I'm able to transmit more bits per symbol. At every time instant, I can transmit only one symbol. So more number of bits I can stuff into it and have more throughput. Okay. These symbols, they can either be complex or real symbols. Okay. Now the second part, pulse shaping filter. So pulse shape is the form of symbols in the signals plane as defined by the pulse shaping filter. The shape of this filters determines how the symbol energy is spread over the time and Fourier domains. So if a signal is more spread in one domain, then we know that from Fourier transform, you would have, in fact, you would have signal. But if it is more spread in one domain, then it is more localized in the other domain. Thus, it has an important effect on the signal characteristic. So this pulse shape is very, very important for us. Okay, so while choosing which pulse shaping filter use, I should be very careful because it is defining my characteristic. The classification of pulse shaping filter. If the prototype filter employed at the receiver, so at the transmitter, recall that I have called it as a synthesis function. So at the receiver, we call it analysis function because we again we will be using an IFFT and at FFT at the receiver. FFT means from the time domain again I'm going back to the frequency domain. Okay, so that's why we refer it as analysis function. In the transmitter, I'm using an IFFT, so we refer it as a synthesis function. So if both of these filters, if they are same, then I refer it as a matched filter. So I can classify these pulse shaping filters in terms of filter matching. I have already studied that matched filters, they maximize the SNR, okay, in a single user scenario. Okay. On the contrary, one may use the different prototype filters at the transmitter and receiver. In that case, you don't have. Second classification, it is in terms of orthogonality. If the synthesis of functions and the analysis of functions, if their inner product they respect the orthogonality condition, I think you already know what the orthogonality condition is. Try to see if two functions, if they are correlated or not. Okay, so that I can try to see from orthogonality from the product I'll be taking. So If both are same, then I will be having some non-zero value. Both are not identical, then I'll zero. Okay, so I can try to understand from this orthogonality. Orthogonal schemes dictate to the use of same prototype filter. If I'm using same prototype filters, means if GMN is equal to H of KL, then obviously orthogonality condition will readily be satisfied. Apart from the filter matching, I'm also immediately having orthogonality also coming into the picture. Okay. Then I have one more set of schemes which we refer them as bi-orthogonal schemes. This we use them for the for where I am having dispersive channels, instead of flat fading or slow fading. If I have severe fading characteristics, where I can more time dispersion or dispersion, then it is better to go for bi-orthogonal. So then I can also classify this pulse shaping filters in terms of localization. So the localization means I try to see how much localized the energy time domain or frequency domain, how much localized it is. Okay, so that I try to see by calculating the variance of the energy in each domain. So the formulae are given here. Then I try to verify this condition. If this product here, if it is approaching to the infinity, then it is a non-localized filter. Else it is a localized filter. Then we go for the last element, lattice. Lattice corresponds to an algebraic set generated by sampling the time frequency dimensions. The locations of samples define the coordinates of the filter, the time frequency. Some people who are already working with the 4G LT seeing this two-dimensional grid where we define the resource blocks, the resource elements. The y-axis I have the frequency, x-axis I have the time. Okay, so this is what lattice means. The modulated pulses are then placed into the time frequency based on the locations of the sample. Furthermore, lattice can be exploited by including additional dimensions such as space. Okay, so already I have two dimensions, which is time and frequency. I can add another dimension, which is space. So a brief overview of lattice concepts. I want to go too much into it. A lattice can be described mathematically by a non-unique matrix. Okay. The lattice geometry identifies the distance between any two lattice points. It can either have a rectangular or pattern or a cancunx pattern or some other pattern also. And then based on this matrix, I can try to find out if the density is undersampled case or critically sampled or oversampled. Then I can say if I am placing my signal with respect to the density, the lattice. There is a very important theorem called Dalian-Low theorem. So if anybody is involved in the waveform design, this theorem you should never forget in life. It says that there is no well localized function both in time and frequency domain for a Gabor basis with lattice density equal to 1. Okay, Gabor basis means we have seen that functions, that a Gabor of functions or the set of the pulse shaping filters which we have seen in right. So I cannot achieve localization both in time and frequency. If I aim at localization in time, I have to sacrifice in frequency. Since spectrum is a very costly thing for me, in general we try to be localized more in the frequency. then in the time the symbols will be having, they will be overlapping each other, so they will be having overlapped. I have to deal with it at the receiver. So in the staggering, I can go for lattice staggering also. Means instead of rectangular geometry, I can also have a hexagonal geometry where I can stagger the real part and the imaginary part. Means if I have, like, if I am transmitting each signal, means each symbol, one complex symbol, time duration, particular time duration, for a symbol P3. Instead of that, for every t/2, I will be sending either the real part or imaginary part. Then at the end of t, I have transmitted both, right? Both real part and imaginary part I have. So for the receiver, it may look same. The previous case, I am sending complex symbols. The second case, I am sending the only the real symbols. Means even the complex part I am taking, I am removing j, so I have just only some real number there. I am transmitting. So what I'm doing, instead of transmitting symbols, complex symbols same time, I'm splitting it in, by time dimension. Then I am sending one thing before and the second later. This we refer it as staggering. Okay, so some example is given here. So we know that a complex number, I can sine plane and cosine plane. This, so in that plane, so I have both the real part and the imaginary part there. So you see that here, suppose if I keep the real part here, then imaginary part I will not be keeping point in the lattice. Okay, I will be keeping it some other point, and you can see here I kept it 1 and 3 here. 2 and 4 I kept them free here. Here I am using those locations. 2 and 4 I am using for imaginary part. So it is 1 and 2. Then in the next instant I am taking 2 and 4. Again 1 and 1. 1 and 3. Then 2 and 4. Again 1 and 3. 2 and 4. So I am doing some staggering. Likewise, I am doing it for the imaginary part also. So it is already proved that I can maintain orthogonality if I respect this condition here. So I can have both the Nyquist rate and also the orthogonality if I keep my tau naught, which is equal to 1 by 2v naught. So that's why we have to transmit these real symbols at a time instant t/2 if I want to transmit as real symbols. So this thing you should come into your mind. Whenever I'm using lattice staggering, then my symbols are real in, and the transmission time, it is instead of full symbol period, it is half the symbol period. Okay? So based on all this classification, so I can classify my modulation schemes. So for the filter, lattice, and symbols. For the filter, I have orthogonal, non-orthogonal, and bi-orthogonal filter. It can be matched or unmatched, localized or localized. Likewise, lattice, I can classify them according to their G. Also according to the orthogonality. If I am having lattice staggering, then my orthogonality will be in the real domain. It will not be in the complex domain. If I'm going for a regular geometry, rectangular lattice, then orthogonality is the complex domain. For example, for the Ofdm, its orthogonality is a complex domain. By symbols, they can be real or complex. My data which I want to transmit, it can be finite number of elements or infinite number of elements. Finite number means, suppose I'm giving this lecture here, it will stop. I will stop after some time. Whereas some Hubble telescope, it is taking some pictures and sending some infinitely large number of elements until something goes wrong with that satellite. data to transmit can be or infinitely large. So we have some different orthogonal schemes. Have like plane WaveDM we have in the plane wave. In order to deal with the multipath scenario, we try to pad them with zeros. Okay, if we don't pad them with zeros, we will be the density lattice density 1. It means OFDM means you see that in the time domain I'm having there are filters. Frequency domain, they are the spectrum will for each subcarrier it will be a sinc function. So that this duality. Okay, so when I zero pad them, then I am reducing the lattice density, but it will by reducing that I can combat the impairments of a multipath channel fading. Then I can go for filtered multitone. In FMT, the filters do not overlap in the frequency domain. Guard bands between the subcarriers can be, they are not overlapping in the frequency domain means they may overlap in the time domain. Okay, so guard bands between the subcarriers can be filter localization in frequency. By doing that, I am on overlap. No specific filter is associated with FMT. You may find n number of. Then you have lattice wave. It is the optimum orthogonal scheme for time and frequency dispersive channels. The symbols are lattice. Okay, and also it releases different lattice geometries, orthogonalized, Gaussian, pulse. Then I have few more orthogonal schemes with the lattice staggering, which we staggered multi, also cosine schemes. The symbols are real numbers. See the moment I'm talking about staggered, it means symbols are lattice staggering, applying orthogonal. So real numbers means original symbol may be a complex number, but I can at one instant I may be sending the real part, second instant I imaginary part. It can be in that. Okay. Lattice staggering is also popularly referred as staggered modulation or offset QAM, OQAM. Okay, a lot if somebody. Both are structurally similar and differ only in the modulation type. For the staggered multitone, it uses QAM, and the cosine multitone is dedicated for the vestigial sideband modulation. It is possible to synthesize one form from another by applying a frequency shift operation and proper symbol placement. Both from one particular modulation I can get. Then we have bi-orthogonal multi-carrier modulation. Most popular one is this cyclic prefix OFDM, which we are using it. When we say OFDM, actually we are using CP OFDM. So we will be copy pasting some part of my OFDM symbol to deal with the fading. Because of that, instead of zeros, now I am filling them with some part of my symbol. So then I am increasing the density of my lattice. So it results in a longer rectangular filter at the transmitter compared to the one at the receiver. As the unmatched filter. But the advantage is simple equalization and simple synchronization. Single tap equalization. Then we have filtered OFDM, where the OFDM is filtered to smooth out the out of band radiation. If the windowing is performed with an additional guard band, a bi-orthogonal obtained. Then we have bi-orthogonal FDM called as BFD. So CPOFDM that does not treat the time and frequency dispersions equally on the doubly dispersive channel. Have both time and frequency. So BFDM with properly designed filters can tackle double dispersion. Then we have non-orthogonal MC scheme, so such as generalized FDM, which allows a correlation between the points in lattice in order to be able to utilize well-localized filters for unit lattice. Also, we have some popular non-orthogonal MC schemes faster than Nyquist, maybe currency IDs. We have partial response for WH frame. For the GFDM at the receiver, we have to use cancellation. So multi-carrier schemes with the spreading approach we have. So spreading is commonly used to reduce APR, which the modulation symbols are mapped to the lattice. Can be interpreted as to considering another gabber system that spreads the energy of the modulation system. Most popular one is, and there exists one more version where if I want to have orthogonality in the real domain, means lattice staggering, then prefer instead of OFDM, we call it as FBM. So I can do spreading for FBMC. So we have like a brief overview of the schemes already existing OFDM and the spreaded OFDM, the DFT spread OFDM or SE, and the multi-carrier waveforms with staggering, which refer as staggered multi-tone or FBMC OQAM. So we can see that in terms of complexity, we see that OFDM, it has only one tap equalization, but for other ones like FBMC, I have to put synthesis and analysis filter. For DFT spread OFDM, the only thing that I will be having just one spreading a function I for my time. But the advantage of a filtered bank multi-carrier signal, they work excellent with ideal power amplifier. Whereas OFDM, I cannot use the word excellent. It will be good if there is user asynchronism. It will be really bad if there is no synchronism. And also for the MIMO support, OFDM can support it very easily, which is straightforward. For the FBMC, a little bit complicated because I don't have luxury of. There are remain criteria. So for the key design features of waveforms for 5G, so these are the things we have to keep it in mind. So in which domain I want the orthogonality, complex domain, real domain, or I want to get away with the orthogonality altogether. And also, do I want to have the cyclic prefix or not? I'm having some synthesis or not? What kind of convolution I'm having? So filtering means you can see it as a convolution operation. For example, you don't require because it has a rectangular filter. Whereas in the case of FBMC OQAM, I have to do linear convolution. Also, filtering granularity. For CPU FDM, I don't have that whereas for FBMC OQAM, I am filtering each subcarrier. Here it is the whole band, the complete band I am filtering. Here each subcarrier I am filtering. That's why we use the word filtered bank multi-carrier. So some of the references I have taken. So this is the reference from the team. part of France. It was actively involved in 5G wave, popularly known. And I found one more about a survey of have any more doubts. So, are you having any questions? Hello?
Yes, sir.
Yeah. So you're already having any then well. So thank you very much.
It was
for-
nice presentation, sir.
Thank you very much. So thank you, IEEE Vizag based section. So I hope that now those who are working on 5G communication or interested to work on 5G communication, that the waveform design. So you have got some basic understanding, good tools to work with. Thank you very much. Sadasivani sir, are you there? Stopping. Okay, I think people can leave. Thank you. Thank you everyone. So that doubts you.
Thank you, sir.
Thank you.